All right, here's our video today. It's the Copenhagen interpretation of reality. And it's just quantum mechanics we're talking about here. Just a brief primer on quantum mechanics. And this is one interpretation. There's other interpretations like the pilot wave interpretation and the MWF, which is the magic, not the magic, but the many world theory, like multiverses. So we're just going to talk about the Copenhagen interpretation, and this is the key one, the one that's mostly accepted. And the reason why it's Copenhagen is because obviously there has been big developments in quantum mechanics that took place in Copenhagen with Niels Bohr and Heisenberg and Pauli, to name a couple. So quantum mechanics could get into some deep math, but this is just a primer to get you an introduction to the interpretation of this reality. So again, we're going to be talking about quantum mechanics, and it's a branch of physics, and it deals with the subatomic level. So let's write it up here. Get my pen working today. Doesn't want to work today. Let me fix it. Let's see if it works now, right? So when we talk about quantum mechanics, right over here, quantum mechanics, quantum physics, whatever you want to call it, it's dealing with the subatomic world. The world of electrons and protons and so forth, neutrons. So it kind of studies how these particles behave. So we have to know this one word to come right from the start. It's called superposition. And when you're looking at quantum mechanics, when you study it, you'll notice that it's very strange. It seems weird. Even Einstein couldn't. Well, he could understand it, but he didn't think it was possible. He said God doesn't play with dice, one of his quotes. So with superposition, basically, I'll write over here, particles, and the particles we're talking about, the particles of the electrons and the neutrons and the protons and the photons. Particles, and we'll just say like electrons, because we're going to talk about the atom with the electrons. So particles like electrons, here's where it gets weird. They can exist in multiple states. Multiple states at the same time. Just think of us existing in at the same time, and we're in Brooklyn, we're in Los Angeles, we're downtown St. Petersburg, all at the same time. Imagine that. Well, that's kind of what superposition is. So they exist in these multiple states at the same time until they are measured, or they are observed. They are measured. Will we fit it? Yes. So that's what. So think about it like this. Let's say you flip a coin and it's spinning in the air. It lands in your hand. You're holding it down so no one sees the coin. So in superposition, we could say that the coin is either heads or tails. But in quantum mechanics, we say no. It's both until it's observed. Until you lift your hand, it's both heads and tails. That's what a very basic introduction to quantum mechanics and the Copenhagen interpretation. Now, it must be said, though, that this superposition happens in the subatomic world. So we don't see it happening in the world that we'll call the macro world, our world. Let me get a clean page and show you a Bohr model of an atom. So I told you about Niels Bohr before, B-O-H-R, Niels Bohr. He came up with a diagram, a simplified diagram of how atoms would look. And even though they don't behave like this is a good teaching model, so you would learn this in school. So let's just take hydrogen, H for hydrogen. Hydrogen has one proton in its nucleus, and let's just change the color. We'll put one electron there. And this is right here, you could call it an orbit, but it's not really orbiting. Some people call it a shell, an energy level. We'll call it a cloud or a ring. You can hear all these names for this circle. But the electron is not going around the proton going around the nucleus like planets orbit the sun. It's not doing that. So it's not deterministic. That's a word we'll talk about when we're talking about Newtonian physics, the physics of the macro world, our world. It's deterministic. But in the quantum mechanics, it's not. So the electron is not going around. It's not just orbiting. It's not doing that at all. What it's doing, though, is pretty strange. It's in different locations around the atom, all at once. They're in quantum states. So we can say this one electron, the electron, because hydrogen only has one electron, the electron is in a quantum state. So around here, in this shell, in this cloud, it could be here, 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 here. It could be anywhere. And in fact, it is anywhere. It's everywhere around the cloud all at once until it's measured. Let's get another picture here. Let me just put a line here to add this. So they're popping in and out everywhere on the cloud. Everywhere on the cloud, on the energy level. And hydrogen only has one energy level. So to say this, though, is a misnomer, because it's not popping in and out everywhere on the cloud, because it is everywhere on the cloud until it is measured. So that's very important to know. They are everywhere along the cloud at once until observed. So that's superposition. And if you can think of it in the macro world, just think if we had a maze with a mouse in it. Draw a maze here. You know, there's a maze. You got to get through the maze. Who knows? There's a road there, and there's a road there, whatever, going this way. Wherever the maze leads us to, you know, maybe there's a dead end here. Who knows? Just a maze. And if you think of a mouse in the maze, there's our mouse. The mouse could be everywhere at once in the maze. It's a bad maze. Got to get a better picture. There we go. Remind me never to try to draw a maze again. But again, so here we have a mouse in a maze, and if we can think of this in the subatomic world, if the mouse was an electron, it could be everywhere all at once in this maze. So it's at the start, it's at the finish, it's everywhere until it's observed, and we just observed it. There it is in that section, looking for its cheese. So when we do measure it, the process, what happens is when superposition collapses, I'll write it over here, when superposition, see if I can fit it in there, when superposition collapses, it's called, it goes into one state. One state. In this case, there's the one state right there. And this process, the process is called the collapse. Where will we fit this one in? The collapse of the wave function. I guess it's not fitting it there, so let's write it here, the wave function. The collapse of the wave function. That's when something is observed. So in the Copenhagen interpretation of quantum mechanics, observation, let's write it over here, observation is key. It's all about observing. Observation can change the state of the system. Very important to know. All right, let me clear that out. Find my clear all button. And there's the first three elements on the periodic table. Row 1 has hydrogen and helium. Then row 2, in the alkalis, you have lithium over there. So as you can see, in this Bohr model, it seems like they're revolving around the nucleus, which they're not. They're just existing in different states all at once. So you may have heard this before. If a tree falls in a forest and no one is around to hear it, does it make a sound? So according to the Copenhagen interpretation, the event could exist in superposition of states regarding the sound. So until someone, in the Copenhagen interpretation, until someone picks up those sound waves, and by the way, any observer, any entity, from an ant to Aunt Sally, right, from an insect to a human, doesn't matter. Any observer, according to Copenhagen interpretation in quantum mechanics, but in Newtonian physics, the physics you learn in school, in high school, until you get into college, will classify the sound waves, would say that those sound waves will be created regardless of whether someone is there. So there is this disconnect between Newtonian physics, in a sense, and quantum mechanics. And keep in mind that when we're talking about quantum mechanics, we are talking about the subatomic level. So let's just get a little chart here, see if we can understand it a little more. So if we look at the macro world, our world, the macro world, and then we'll look at the quantum world. And in the macro world, it's deterministic. It's there, right? We know the tree's there. We know if we cut it, it's going to fall. In fact, we can predict where it's going to fall. But in the quantum world, it's not deterministic. It's probabilistic. Or I should say probabilistic. Say that 3 times. Probabilistic, deterministic. In other words, everything's in a state of superposition until it's measured and where the wave function will collapse. And the two do exist, though. In quantum, though, it's all about observation. In order for the superposition or the wave function to collapse, something needs to be observed. In a deterministic macro world, something can happen regardless if someone sees it. So we do know that in the macro world is based on quantum mechanics because we're all made of matter. So all that matter then at subatomic level is governed by the quantum world. So the two do exist. So we can say that events, in a sense, are governed by quantum behavior. So this is just a basic introduction. We'll talk more about quantum mechanics and the other interpretations in other videos.